Okay, today we're going to talk a little bit about reciprocal space, first Brillouin zone, and k-space in tech that allows us not to use k-points file each time and calculate um, once k-space in number and use the number afterwards with larger structures. And actually, we should after some period of time or after dramatic change of unit cell, recalculate that number to be sure that we are in the relatively good intervals of k points. So what k spacing is actually is, well, let's just have a look at the page with k spacing tag, and they will give us a formula which is maximum whether of 1 or that number. Let's rewrite the formula. So n is number of k points that we will have um, in our calculations, and it is maximum of two numbers, 1 or some number divided by k spacing. And well, if we didn't forget about that yet, the formula that gives us b, for example, b1 is a2 multiplied by a3 and divided by a1, scalar multiplication here, and a2 and a3. That number is the volume of the unit cell, and here uh, let's have a look to better understand how that transformation happens and what we should know about the transformation from direct space when we have meters to reciprocal space when we have meters meters to the power of -1. So it is obvious from that formula. There is a meter square, meter cube, so that will give us meter to the power of -1. Um, so let's have a look on some unit cell. 1, 2, and let that angle will be equal to 90 degrees to that angle, to that vector, and it is these vectors are a1, a2, and a3. And unit cell itself should have such kind of shape. And yeah, well, again, if we translate that unit cell in one of that directions to the value that is equal to absolute number of that vector, we will have absolutely the same unit cell, just that starts here, and for example, properties here and here will be equal because we just translated that vector, and everything should be translated and equal. And distance between these 2 points is equal to that a1 vector. So let's start to transform it into unit cell, but in reciprocal space. So this is our first formula, and B1 should be something like A1, but in reciprocal space. Again, this is just the number V, and here is a vector multiplication of A2 and A3. So A2 is here and A3 is here as well. Let's have a look. And A2, A3. So according to all of that vector multiplication of vectors, the final vector should be perpendicular to both of them. So that vector should be perpendicular to that plane, and the direction of that vector should be, if we have such rotation, so we multiply a2 by a3, so a2 by a3, and final vector should look at us. So that means that the vector is out of that monitor and looks at us, whereas let's say if our vectors were something like that, a2 and a3, we would have clockwise rotation, and final vector would be directed out of that plane and out of our space, so it will look into monitor. Yeah, so that vector, so due to the fact that a2 is perpendicular here, and let's say that here we also have 90 degrees, and that vector will be parallel to, so b1, that vector b1 will be parallel to a1 because they are both perpendicular to a2 and a3. What else can we say? Actually, there should be 2 pi. Sorry, I forgot about that. And what happens if our vectors are larger than p2? Absolute value of our vectors are larger than 2 pi. So if a2 multiplied by a3 is larger than 2 pi, it will mean that actually a2 and a3 they themselves don't have any, doesn't make any sense because they are roughly cancel each other here and here, but I will not do that because well, it is, I don't know, is it correct just to cancel them like that. So just let's have that into account, and roughly we have something like that 2 pi divided by a1 b1. And you can see that there is reverse uh, dependence of those values. So that means that if a2 increase, b1 decrease, or oppositely, if a1 decrease, if a1 decrease, b1 increase. And well, if absolute value of that a1 is larger than 2 pi, that means that vector b1 is less than vector a1, or oppositely, if a1 is absolute value of a1 is smaller than 2 pi, less than 2 pi, it will mean that b1 in reciprocal space is larger than a1. So let's say here that a1 is larger than 2 pi, and we will have our first vector in reciprocal space. Uh, that is, so a1 is less than 2 pi. It means that b1 should be larger, yeah. So they should be parallel here. So b1 should be perpendicular to a2 and a3, and it will look something like that. And let's show that uh, b2, also b1 is a bit larger than a1. Well, in case of other vectors, we just uh, continue to do such things, and well, b2 will be equal to 2 pi. Here should be a multiplication of a3, a1. Well, let's check. Let's check. Yeah, a3 and a1. And that means here we'll have b2 and, oh, sorry, a2, and here should be a3, a1. Again, this is the volume, but absolute value of that multiplication should be equal to absolute value of that multiplication. And well, just to make that easier, let's imagine that they cancel each other. Well, actually, we should do it in more formal way, but obviously that in the end they will cancel each other. So here is a2, and again, let's imagine that a2 here is larger than 2 pi. So a2 is larger than 2 pi, and that will mean that means that vector in reciprocal space will have will be shorter, but I didn't draw draw it here correctly, because here obviously that angle is not 90 degrees, and so here angle is 90 degrees, but here is not, and well, it should be 90 degrees, and thus it should be something like that. Yeah, maybe like that, and yeah, that how B2 looks. And yeah, let's redraw it here, so it is shorter than A2, and A3, let A3 will be equal to pi, so they will be A3 will be B3 will be equal to unity, and it is not well larger or shorter, and it is just equal with some coefficient. Uh, so here so B3 is equal to something like uh, here we had A1. Let's check A1 and A2. Okay, so it will be equal to A1 A2 to pi divided by volume. Uh, A1 and A2. So we have A1 and A2. And we have that plane, and our vector should be perpendicular to that. And yeah, we said that A3 is equal. Yeah, so let B3 should be something like that, and here it will look like that. Well, actually, well, it is there is now 180 degrees. There is 90 degrees, and yeah, and here is also 90 degrees. So let's say that it is 90 degrees, and this is our vector B3. This is B2. Well, if we somehow rotate that uh, vectors in reciprocal space, it should look something like that. And as you can see, here we had um, here the angle was less than 90 degrees, but in reciprocal space that angle increased, and the angle is equal to some number that is obviously more than 90 degrees. And yeah, that is what happens. Vectors that are long in direct space becomes uh, less uh, and becomes shorter, and so on. And angles as well becomes um, narrow angles here becomes wider in the reciprocal space. So that we should have into account when we calculate that number, and when we use k-spacing in our calculations. So let me remove that beautiful draws, and uh, well, having all of that into account, um, n will be equal to maximum of whether of one or that number. Um, let's say that b absolute value of b1 is 3, and k-spacing is equal to 1. Well, obviously we will have 3, and that is our number of k points in our unit cell. Let's say that uh, K-spacing is 0.5, that is the default number of K points, and here we'll have 0.5 as well, and thus we have 6 uh, K points in reciprocal space. And as you can see, by decreasing that uh, number of amount of quantity of uh, K points in reciprocal space in reciprocal unit cell decreases, and that will mean here we have 0.25, 6, 12. So we have 12 here, and well, we should keep going until some number when we will have some kind of stable number of energy after increasing of number of K points, accuracy of our calculations is not increase. Yeah, so here should be energy should be negative here, and this is K points, and if with 1 K point we have some value in our Aussie car, here let it be equal to 6, we'll have such number, and at some number here we will have more or less uh, stable line here, and that number we will use. So here will be some amount of K points that is respective to some number of K spacing, and that K spacing we can use in our future calculations. And let's say when we increase that number by 9 and with some K spacing, amount of K points will increase automatically because, well, when you have um, a number of number of K points should increase automatically, and um, BI divided by K spacing. So if in real space we have really big unit cell, number of K points should be less. Something is wrong here. Let's check another time. N is calculated as S divided by BI, BI divided to pi multiplied by K spacing. And BI is smallest allowed spacing between K points in units of angstrom minus 1. The number of K points increases when the spacing is decreased. The number of K points in the direction of the first, second, and third reciprocal lattice vector is determined by... Oh yeah, everything is fine. So B1 is actually, yeah, let's say B1. So here we have formula for B1, and when we increase that A from 3 to 9, B will decrease, and we will have here not 9 but 1. And here instead of 6 will have only 2 key points, and yeah, uh, when we increase our unit cell in direct uh, space, in real space, we should use less key points, and that is the aim of all of that formalism, and that helps us uh, to calculate large structures. So we shouldn't linearly increase number of key points with increasing of real unit cell. Um, yeah, so what we should know about case spacing. Now let's move to direct and to Brillouin zones. So let's imagine that we had some kind of, let's say, something something like that, and, let it be um, unit cell in two-dimensional unit cell in direct space. So if you do remember all of that rules, when narrow angles becomes larger, wider uh, angles in reciprocal space, and shorter vectors becomes larger, and larger vectors becomes shorter, and we will have such uh, unit cell in the reciprocal space. And let's multiply that uh, unit cells, and there should be a law to define. There is a law and rules to define first Brillouin zone. So um, it is 4, maybe in our case 4. Well, we can add as much as we can, but there is no need because our structure is quite simple and it is two-dimensional. Here we have 4 unit cells, and so let's have a look to that node, and let's connect that node to the closest neighboring nodes by lines, and so let's connect that node to that node, and insert perpendicular plane in the middle of the line that connects to dots, to nodes. And so we can imagine here another line that connects those nodes, and middle of this node should be somewhere here, and you also should have a line that looks something like that, and here a line is here, and the middle of the line is here, and that plane should be perpendicular to that line that connects to nodes. Here we have middle of the line here, and it will be perpendicular. Perpendicular line should be something like that. And here we have another line. Middle of the line is here. Let's insert some some plane that is perpendicular to that connecting line. And here we have our final um, connecting line. So here we have another line, another node, and but middle of the line is here, and if we insert the plane, it will not cross our first Brillouin zone. So why does it called first Brillouin zone? Because we have chosen the first closest to the node other nodes. Second Brillouin zone will be some figure that is made from the second neighboring nodes. Um, yeah, so that is how it works. And uh, when we calculate band structure, we have high symmetry points in that Brillouin zone, and so obviously the first high symmetry point is that node, and that that point is called gamma, and it has um, 0, 0, 0 coordinates. Um, and there are other high symmetry points. In that case, is when you don't know high symmetry points, it's always useful to go to online resources. One of them is that website. When you just choose your software and your uh, unit cell. So let's use that unit cell and calculate the structure and high symmetry points. So this is my unit cell, which is multiplied by 2 in each direction. So you can look at the supercell, and this is the first Brillouin zone, but in 3 dimensions. So here in 2 dimensions, it looks like that for that unit cell. For my unit cell, which is long in that direction, in reciprocal space, it will be short in that direction, and those short uh, vectors will be really large in reciprocal space. And in articles, you can see that they use, I don't know, is here pen structure or no. So let's say maybe that one. Yes, so if you can see here are those high symmetry points, and obviously gamma is here, and we have other high symmetry points, and that website gives you all of the high symmetry points, all of the standard high symmetry points, and you can use it in we should use it in our kpoints file, but kpoints file can be written in different ways. In our case, we should use line mode. So here we had automatic mesh when we uh, gave to the wasp some numbers, and it automatically uh, built that mesh. In our case, in case of band structure calculations, you should uh, you should go to the line mode. So example is here, and let's copy that file, that rows, and let's use it in our calculations. Uh, so this is a bulk. Yeah, that should be right. Make directory band structure. Nothing is here. Let's create kpoints file and insert that lines. So this is the comment line. Let's say that we want, let's say 200 kpoints between each case high symmetry points. So between gamma and x, we will have 200 kpoints, and that will give us really smooth band structure. But do we need these numbers or not? So actually, I think that I already have points, but let's do it again. We don't need too many key points. So we should start with, let's say, V. Let's start with V and go to gamma, and from gamma to C, or yeah, to gamma, from gamma to C, from C to A, from C to A, and from A back to V. Yeah, that should be pretty nice. And where is V? So V is here. Let's just copy it here, and I think it will be useful to just move it here. Yeah. Will not remove gamma yet. So here is V. Here is a gamma. So see second high symmetry point is gamma. So it goes from V to gamma, and between V and gamma we will have 200 kpoints. Between gamma and C we will have 200 kpoints as well. And let's just insert it here, and this is a C. So we should use that number again to show WASP that we want another set of high symmetry points from C to A. From C to A. From C to A. And from A to V again here. So V is 0.5. Okay, let it be from 0.5 to V. And let's add another line. I just wanted to calculate from V to minus 0.5, and it will be with dash. Oh, we have quite a lot of lines, and let's decrease that number to 150. Right. Okay, so here we have our kpoints file, and in next video I will show how to calculate band structure.